And let me go ahead and introduce our speaker. So this is the first Statistical and Nonlinear Physics lecture of 2021. We started in June of 2020, and we have made it through a whole bunch of incredible talks, almost all of which are on YouTube. I think two were problematic because of my own fault of being unable to tape them. Our speaker today is a very, very special guest, Professor Robert Swendsen, Bob Swendsen from Physics Department at Carnegie Mellon University. And the title of his talk is The Definition of Entropy in Statistical Mechanics. I don't want to steal the thunder, but I should say a few words about Bob Swendsen. He received his BS in physics from Yale and his PhD from University of Pennsylvania. He did his postdoctoral work at University of Cologne in Germany and the Kernforschungsanlage in Jülich, Germany. I learned German in 1977 and Brookhaven National Lab. In 1978, he joined IBM Zurich Research Center. In 1984, he became a professor at Carnegie Mellon University. He subsequently also held positions there as head of the physics department and associate dean of the Mellon College of Science. Professor Swendsen has worked on the development of the Monte Carlo renormalization group method, cluster methods for computer simulations of phase transitions, histogram methods for the analysis of data from simulations, and optimization methods for the simulation of complex systems. He has also written two books, Dan Mattis and Bob Swendsen, Statistical Mechanics Made Simple, second edition, World Scientific 2008. And Bob Swendsen, An Introduction to Statistical Mechanics and Thermodynamics, Oxford, London, 2012, and a second edition just came out in 2020. Professor Swendsen is a fellow of both the American Physical Society and the American Association for the Advancement of Science. He was given an IBM Outstanding Achievement Award in 1981 and shared a Forefronts of Large-Scale Computing Problems Award with Kumar, Rosenberg, and Coleman in 1991. He is the recipient of the 2014 Anisur Rahman Prize for Computational Physics. So please welcome Bob Swendsen. Thank you so much for joining us, and the floor is yours.
Thank you very much. That's a very kind introduction. I appreciate it. I'd like to thank you for inviting me to this virtual colloquium here. The topic I've chosen, the definition of thermodynamic entropy in statistical mechanics, should actually, I realize, be a very boring one because we've been discussing among physicists what the definition of entropy in statistical mechanics is for about 150 years. And we should have come to some conclusion by now. There should be a consensus. There isn't, which is unfortunate. I'm going to talk today about the situation there only for classical mechanics. It's hard enough as it is. And most of the problems that occur in general statistical mechanics are all there in classical mechanics. Now, during the last 150 years, there has been a little crystallization of opinion, it was not consensus, but crystallization of opinion, so that people agree on some features of the problem. So it occurs to me that I possibly could use a subtitle here. Whoops.
Can you use the arrow, the right arrow?
Yes, I did.
Oh.
I get, well, anyway. And it occurs to me that dogma versus heresy is a good description of what I will talk about. there is not a single dogma. There are many because people have different opinions. They agree on some things, they disagree on other things. And I'll try to explain why that is and tell you a little about it. This is my personal view, very biased, but that makes it more fun. Now, the traditional definition of entropy is this: it's S equals K log W. Um, what is that founded on? Well, perhaps it's because it's on Boltzmann's gravestone. Uh, that would seem to be a fairly good reason because it's inscribed in stone. You can see it at the top of the screen, S equals K log W. And and you can also see Boltzmann. Boltzmann, by the way, looks much sterner in this picture than he actually was. He was a very kind man. Uh, he liked to read Schiller. He liked to go to opera. He liked to drink beer and a free glass of wine now and then. Great sense of humor, but he looks very serious here. This gravestone, by the way, was completed in late 1920s, whereas he died in 1906. So it was more than 20 years after his death, and his remains had to be moved to a new site so that they would be here. Um, Now, this definition of entropy that you can see there, S equals K log W, it requires some explanation of what these terms mean. So, K is a constant, which is now written K sub B. It's Boltzmann's constant. It is interesting, among other reasons, that Boltzmann never used it. He always considered a dimensionless entropy, so he would not have recognized that. Log at the time, log was used for the natural logarithm. Now it's usually ln, but what is intended here is the natural logarithm. Then we come to w, and w stands for the German word Wahrscheinlichkeit, which means probability. Uh, the equation was written originally. Um, well, yeah. Let me start. Most physicists do not believe that W means probability, but instead believe that it means a volume in phase space. Uh, whoops. But there's a problem with this interpretation. So if we consider a volume in phase space, the problem is Liouville's theorem. And Liouville's theorem states that the phase space distribution is a constant along the trajectories of the system. So as the system develops, it takes a little bit of volume with it, and that volume doesn't change. That means that that the shape of a volume in phase space might change dramatically, and it will, but the magnitude of the volume will not. Well, this is a problem because if W is a volume in phase space, then any expression for entropy using W will also be a constant. That's a violation of the second law in thermodynamics. So that is a problem. I'd like to discuss the free expansion of an ideal gas to give you an idea of the magnitude of the problem and what is involved here. So if we look at a long cylinder of length L and uniform cross section and put in a little wall at L0, And then we can fill the left between 0 and L0 by a fill it with an ideal gas. So this is a gas. It's an ideal gas is magenta apparently, but anyway, that's where it is. And on the right is vacuum between L0 and L. There are N one equals N atoms in the gas and 0 in the vacuum. Now at t equals 0, we remove the wall at x equals L0. It will have x going from 0 to L0. And we get the following picture. The dashed line in the bottom is just where the old wall was before it was removed. And as you can see, the ideal gas is spread over the entire volume. You have N1 equals N over L, NL over L, excuse me, NL0 over L, particles in the left, and the remaining in the right. So that's what we see. Now, if the ideal gas is represented by a volume in phase space, that volume is the same before and after the free expansion. So let's suppose n equals 10 to the 20th, which would be a fairly small system. Um, and L is 10 times L naught. So it expands by a factor of L, a factor of 10. The phase space volume increases by a factor of L over L0 raised to the power n, the number of particles, which in this case is 10 to the 10 to the 20th, which is a very, very large number. So if you look at the density of points after the free expansion, it is 10 to the minus 10 to the 20th times smaller than the density before the free expansion. Well, that is a very sparse distribution. There aren't very many particles there at all. Now, if we try to, the density of points in phase space, if we want to increase the number of particles, we have to increase by this factor of 10 to the 10 to the 20th, which is asking a lot. So what do we do? What can be done about Liouville's theorem? Well, traditionally, there is a solution to this problem. Cheat. The idea is we use a different volume. We use one volume defined one way before we start the expansion, the irreversible process by removing the wall. And then afterwards, we'll use a different volume. So when the system undergoes an irreversible process, we know that the entropy should increase. We use a bigger volume. But don't call it cheating. Call it coarse graining or typicality or interventionalism or something else. The oldest way of cheating on Liouville's theorem was developed by suggested by the Ehrenfests in 1911. It's called coarse graining. It's still quite popular. The idea is it consists of replacing regions of the true volume in phase space by bigger regions in the coarse grained volume. Now remember, the necessary increase in size of the volumes is a factor of 10 to the 10 to the 20th, which is not a small change. A more recent suggestion of cheating in Liouville's theorem is typicality, which is suggested by Leibowitz in 1993. Typicality augments the true trajectories in phase space by including all typical trajectories. That is, all trajectories that look pretty much like the original true trajectory, but they fill this large region of phase space They again increase the size of the volume that you've got to work with by 10 to the 10 to the 20th. There's something similar to that. Still not a small change. Well, in my opinion, this whole thing seems quite ad hoc and unsatisfactory. Um, Although there are a lot of people who think that cross grading is fine and uh, typicality is very popular these days. But perhaps we can go back to the original definition of entropy by Boltzmann in 1877 and see how he solved the problem. Now, everybody cites a particular paper by Ludwig Boltzmann from 1877. The title of that paper is Über die Beziehung zwischen dem zweiten Hauptsatz und der mechanischen Wärmetheorie und der Wahrscheinlichkeitsrechnung respektive den Sätzen über das Wärmegleichgewicht. That's a hell of a title. It's very long and it's characteristic of the paper itself. Almost nobody has read the paper. Everybody cites it, nobody's read it. Why not? Well, it's in German to start with. Um, but that's not the only reason. Generally speaking, the German scientists don't read it either. It's quite involved. It's written in 19th century scientific German. Now, we can't get mad at Ludwig Boltzmann for writing a paper in 19th century scientific German because he was a 19th century scientist in Germany. But it makes it very difficult to read. The vocabulary used is different, and the argument tends to be quite complicated. So, we would like to have an English translation at least, and one has been provided by Sharp and Machinsky, but only in 2015. Now, that's a long time to wait from 1877 to 2015 to get a translation of it. The title in the translation version, the translated title in English, is given here. And most people reading that have a feeling that somehow or other they're still reading German. So it's not easy. The actual translation is a good one, but it is very complicated. Not an easy paper to read. All right. What we have to do, however, is very simple. We have to find S equals K log W or something very close to it and see where that occurs in his paper and how he argues. The problem is that doesn't appear in any of Boltzmann's papers. It was first written by Max Planck in 1900, and now Max Planck is an interesting person to be the interpreter of the statistical mechanics here because before 1900, Max Planck was a molecule denier. He didn't believe in molecules. Ernst Mach didn't believe in molecules, and Max Planck was one of his disciples. Uh, in 1900, Max Planck wrote a very famous paper in which he showed that light was quantized. So light came, as Feynman said, in light was lumpy, and you didn't have any kind of amount of energy. You had certain multiples um, a, of a unit of energy for the light. After Max Planck recognized that he could only explain the black body radiation by assuming that light was lumpy, he decided there wasn't any reason not to assume that matter was also lumpy. So he became a believer and and wrote S equals K log W down. Well, what does Boltzmann's 1877 paper actually say? Well, Boltzmann began by considering a typical irreversible process, which involves an exchange between two thermodynamic systems. Now, if you just have one system and it's in equilibrium, it doesn't do anything. But if you have two or more systems, then things can change. You can release a constraint between these two systems and have something interesting actually happen. So, now this is part of a paragraph that Boltzmann wrote. It occurs in, I think, the second page of his paper. I've split it into three so you can see more easily what he is saying. This is all one paragraph, and in the second part, I've put in three dots because the actual quote goes much longer and doesn't contain anything really essential. So it considers a composite system that is isolated and does not interact with other objects. So that's the first thing that's important. He's considering a composite system, more than one. You see, he defines entropy in terms of more than one system. So his example, first consider a container with absolutely smooth and rigid walls. One half is filled with air at a lower temperature or pressure. The other half is filled with air at a higher temperature or pressure. And this composite system begins in an arbitrary state and by its interactions changes its state. It's fairly wordy. The German word used for pressure, by the way, is tension, which means Spannung, means tension, which makes it difficult to read this thing. But anyway, that's his example. Continues in the same paragraph. According to the second law of thermodynamics, these changes must always increase the total entropy of the entire system. So he's stressing the entire system must change and not the one part or the other, but the whole thing must increase its entropy, as we well know. Now, he then says the initial state will usually be a very improbable one. The system will run from this state to ever more probable states until it reaches the most probable one, which is the state of thermodynamic equilibrium. Okay, he then continues, and the bolding this paragraph, this sentence is my contribution here. If we apply this to the second law, we can identify the quantity that is usually called the entropy with the probability of that state. So this is his connection between entropy and probability. He doesn't bother to specify that it's a logarithm of the probability. That occurs much, much later in the paper. But he then has a connection between the entropy of this composite system and the probability of the state of the composite system. Okay? Now, on the proposed definition of entropy that I'm considering here, which is actually Boltzmann's, uh, has two features to it. One, the entropy is defined for a collection of systems, and I just showed you why I believe that Boltzmann defined it that way. The number of thermodynamic systems is m, and it must be greater than or equal to 2, but there can be arbitrarily many systems in the definition. You can have 3 or 10 or 1,000 or a billion. It doesn't affect the form of the entropy that is finally derived for any individual system. So we'll see it always comes out to be the same expression, whether you're considering two systems or 1,000. The entropy of each of them will be the same. Now, it also wants to consider the macroscopic variables for the m individual systems. And he is going to look at the probability of these variables. So I've got the energies, the volumes, and the number of particles. J goes over the systems 1 to m. Excuse me, the phone just rang and it just stopped. Good. Um, the total energy is the sum of all the energies. And of course, the total energy is a constant, even if I exchange energy between two systems. Similarly, the total volume is a constant, even if I have a um, piston between two systems so they can change the volume. The number of particles, total number is the same because a constant again. So these three quantities on the right are all constants, but the number of particles, nj, can change. We saw it in the example I gave. N1 was n, and N2 was 0, and it changed to N1 was a fraction of the particles, and the rest went over into N2. And T stayed the same. So the individual systems can exchange energy, volume, or particles, or not, as the experimenter chooses. So any two systems can be brought together and allowed to exchange particles. They can then be separated again and two other systems, or three or four, as you wish. Now there's a second feature to the definition. The entropy is defined as the logarithm of the probability of macroscopic variables. Um, these two features, it's a collection of systems and the logarithm of the probability of the macroscopic variables of the systems, all M systems, are used to define the entropy. Now, I'd like to point out that no volume in phase space enters this definition of entropy in any way. And that's also true of Boltzmann's paper. He explicitly at one point denies that the volume in phase space is part of his definition. You don't need it, and you need it not to be there, actually. So let's look at the free expansion of an ideal gas again. This is what it looks like. We start off with the gas in the left-hand side between 0 and L0 and a vacuum in the right. And we remove the wall at x equals 0. So x goes from the left at 0 to the right at L. Fortunately, we can do something with this exactly. We can look at the exact solution for the time-dependent probability of this problem, which for some reason is not generally stated, but it is available. The problem was solved by Hal Frisch in 1958. It's a long time ago. I made some relatively simple comments on his solution. It's all Hal Frisch's solution, not mine. 50 years later, 2008, and the exact solution exists. This is what it looks like. Okay, that's fairly complicated. Now, W of x and t is the probability density of finding particles a distance x from the left-hand side uh, at a time t. The time t only enters in the right, extreme right, in the exponential. It's a Gaussian in time. If t is 0, where everything started, then that factor goes away. It becomes just exponential of 0 is 1. And the sum can be done exactly. And the entire expression on the right is w of x and 0 is equal to 1 over L0, which is the density in the left-hand side. In the right-hand side, on the right-hand side of the partition, it is 0. Uh, if you go to long times, And you see you have t squared over tau squared. Tau is the time for a particle to cross the box. The particles are moving fairly fast. If we have the RMS velocity for a gas at room temperature, it's pretty close to the speed of sound. So this factor, t squared over tau squared, goes to large values fairly quickly. So the exponential of minus pi squared n squared over 2 t squared over tau squared goes to 0 quite rapidly. And consequently, every term in the sum goes to 0. And the whole thing, w of x and t, goes to 1 over L for the entire box. So it goes to a uniform distribution, and it does so rather rapidly. Now, there's something else interesting about this that I'll just mention in passing. It goes to a uniform distribution and stays there. There is no sign of Poincare cycles in this expression. You just don't see them. The reason for that is that the length of time before a Poincare cycle occurs is very, very sensitive to exactly where the initial particles are. And we've assumed that the initial particles are distributed somewhere in the box. And if you average over all possible positions of the particles, as I have in this expression, or Hal Frisch did, you get an impossible to predict when the Poincare cycle will occur. And consequently, all you see is every is a very rare event in which every all the particles will go to the left, or all the particles will go to the right, or all the particles will go to the center, but you will not see anything you can identify as a Poincare cycle. So I'd like to look at this problem from a different point of view. I'd like to look at it now instead of looking at the exact solution. I'd like to look at what this entropy of this classical ideal gas would look like from the definition of entropy that we've just introduced. The two particles, the uh, two systems, many particles, two systems, and considering the probability of the distribution. Well, let's consider only the contributions of the position variables. It's an ideal gas, so the uh, velocities aren't doing very much. And let's distribute the particles among M systems. So what we looked at explicitly was distributing among two systems, but let's generalize this to M systems. And we can consider the probability that we have nj particles in the J system for all of these systems. Well, this is a well-known solution. Um, W is the probability is nt factorial over uh, the product of the nj factorials, and it's multiplied by these volume factors. It is simply the well-known multinomial distribution. There's nothing special about this. This is well known. It's a matter of combinatorics. You get that factor in front, and it's something we've all presented to our students. Well, if I take this equation down at the bottom and I transfer it to the next page, and I can write the expression in a simpler version uh, that I have on the right there, nt factorial over vt to the nt times the product over the systems. Uh, and then I can look at what's going to happen when I take the logarithm of this probability. Well, I get the logarithm of nt over factorial over vt to the nt. It's on the moved it to the second term. And the first term, the sum, the product of in that first equation becomes a sum in the second equation. And that is the logarithm of the probability. Just what I said should be the entropy in the assumptions. And that gives the entropy of this distribution of particles as KB log W. So this is the expression for the entropy. Now, we normally look at the entropy as something that is additive because we're looking at individual systems. If we have two systems, we can add the systems and get the entropy of the total system. This time, however, we're looking at the end from the other end of it, and we have a total entropy. And what we see is that the total entropy can be separated to give the entropies of the individual systems. So we look at the uh, factors in the entropy that depend only on Vj and Nj, and we can separate them out as Sj of Nj. So Sj of Nj is Kb log of Vj over Nj to the Nj over Nj factorial. I should include Vj as a argument, but I'm concentrating on Nj. Now, this is a very interesting expression because, as you see, I've done nothing special with it. I have not invoked quantum mechanics. I have not invoked any particle properties, but the factor of 1 over Nj factorial is in the entropy automatically. It is there for identical classical particles. It is there for distinguishable classical particles. It is just there. And it should be because it is there for um, colloids as well as electrons. So uh, now, this is a special case. This is only the number of particles I'm looking at. Uh, and for general systems, we'll introduce Hamiltonians, interactions between the systems, between the particles, and that's what I'm going to do now. Assume that each system has its own Hamiltonian, and assumes that there are no terms in the total Hamiltonian linking different systems. The total Hamiltonian is then just the sum of the individual Hamiltonians. The probability of the entire systems of all the EJs, VJs, and NJs is given by this expression. The delta function on the right, delta function of EJ minus HJ, specifies that the energy is given by the Hamiltonian. There's a factor of it of a delta function for each system. The dq is the integral over all the particles, the positions, and that's the factor that gives us the volume dependence. dp integrates over all the momenta, and the factor out in front is again from the multinomial distribution. The 1 over omega, capital omega t, is a normalization. We can write this thing in a very obvious way. We can separate it out into getting omega j for each system. The omega t of ET, VT, and NT, of course, is simply a constant. It doesn't do anything else. So the entropy, the total entropy of the system is K log the total probability of the system plus constants we're not interested in. And this can be written as the sum over contributions from each system. So this is the same thing again, and it gives Sj, the entropy of the jth system, is a function of Ej, Vj, and Nj only, not a function of anything else, is K log omega j of EJ, VJ, and NJ, plus a constant. So the total entropy is the sum of all of these entropies plus a constant. And if I evaluate that, this is the function, the form I get for the entropy of a single system. I'd like to call attention to this factor that I've just put in. This is not a necessary factor. H is Planck's constant, and I have included it because that gives me the right limit when I take the classical limit of a quantum mechanic entropy gives me the same thing. It factors out for anything where I consider two uh, interactions between two systems, classical systems with the same dimension. Uh, I'll discuss that more precisely if you're interested, but this is not a volume in phase space. This is simply an integral. It is defined, the entropy is defined through this integral, and that's what it is. I show it on the next slide. Now, there's some interesting features of this. One feature is that I have assumed the energy distribution to be a delta function. Now that's because I've taken the entropy to be defined at the maximum of the probability distribution. This is clearly an approximation, but it's a good one. It is not the exact one. I will discuss a better approximation a little later. But this gives the microcanonical distribution, and this is the entropy in the microcanonical distribution. It assumes that the energy is known exactly. It also assumes that the number of particles is known exactly. Now, if we evaluate this in the microcanonical approximation, we get this expression. Now, I'm sure everybody is familiar with the expression. The energy is raised to the 3n over 2 minus 1, so it's not exactly extensive. There is a factorial of 3n minus 2 over 2 minus 1. There is another factorial of n. There's another n factorial in the second term. It is not an exactly extensive quantity as it should be, because it has been derived for n particles, which are all independent of each other. Each particle should make the same contribution. What's wrong here is the assumption of the microcanonical ensemble. If we look at a general system that has ever been in contact, in thermal contact with another system, any system, if it's been in contact with another system, even if it's now isolated, the energy distribution has a finite width because of that contact. Similarly, if the system has ever been able to exchange particles with another system, this number of particles is not exactly specified, but there's a small range. You can approximate these ranges by looking at the ideal gas entropy in the grand canonical approximation. Instead of the microcanonical, we look at the grand canonical. And what we get is a very interesting result. Instead of depending on NJ, it depends on NJ average, the average of that distribution. Instead of depending on EJ, the specific energy, it depends on UJ, which is the average of EJ. So SJ in this grand canonical approximation is exactly extensive. I'd like to comment that this is an exact derivation for the ideal gas. No use at all has been made of Stirling's approximation. which it normally would be going from the top. Now, this is the definition that we're using. Defined for a collection of systems is defined as a logarithm of the probability of macroscopic variables. No volume in phase space is used at all, anytime, in any way. And now we have a question. What is this? Is this definition dogma or heresy? It is definitely not the usual definition that is used. It's not S equals K log omega, log W. So from the point of view of virtually all books on statistical mechanics and thermodynamics, this is not the dogma. The dogma is, in terms of a volume and phase space, it is heresy. But this is Boltzmann's definition of entropy, not what you normally find in the books on statistical mechanics. So at that point,
may I ask a question?
I'm stopping, and you may ask any question you like.
Okay. You had an expression of integral dpdq and delta function. So isn't it just a volume of the phase space of the equi-energy volume of the phase space?
That it is the integral, which turns out to be a volume of phase space, yes. But
and why do you say it is not related to volume of phase space in any way?
Because it is that integral can be interpreted as a volume in phase space, but it is simply the integral. The volume in phase space related to the entropy does not change when you undergo a excuse me. When you undergo an irreversible transition, this volume will. So you can always interpret any integral as a volume, but it is not the volume that is the volume of particles in phase space. You're technically right. It is a volume, but
isn't it a real space volume?
No. You have a 3n dimensional integral over momenta and a 3n dimensional integral over positions. So 6
the VJ is a real space volume.
The VJs are real space volumes. That's right. Is the volume of system J.
So that brings, first of all, let me congratulate you on a very interesting presentation.
Thank you.
So that brings me to a point that I'd like to make, and that is, so from what we've been doing with Terrell Hill's small system thermodynamics, we agree completely with what you say, that in the grand canonical ensemble, the entropy is exactly extensive. You've taken out the factorial, the Stirling's approximation. That's fantastic. The only thing that I will comment is that by going one step further to take out the fixed volume, which is what Terrell Hill did, you actually end up with a sub-additive entropy. And what that means is that the system prefers to subdivide into a distribution of volumes, which increases the entropy. And therefore, there's a physical reason for this subdivision and an actual physical distribution of these sizes. So I think that's one step further.
That does sound extremely interesting to me. I haven't looked at Terrell Hill's book in quite a long time. I will check that out.
I'll send you a preprint. You know, I've been following your work for quite a while. It's very, very interesting, and I hope you find what we're doing interesting as well. Thank you.
It sounds very interesting. Thank you. I look forward to getting that preprint.
We are now open for discussions, by the way. So you're finished, Bob, right?
Yes.
Yeah. So thank you for a fantastic talk. This really is, I mean, extremely fundamental and very well presented. It also brings in mind some earlier work done by John Ray. I don't know if you knew John Ray from Clemson.
No, I don't think so.
This was back in 80-81 timeframe. Some of this work actually was yeah. So they talked about the grand canonical ensemble being the fundamental ensemble for statistical mechanics.
I think that's correct. Yeah.
And that, yeah. And that is needed for correct Boltzmann counting. So there was a paper on correct Boltzmann counting that John and Will Graben from Clemson had written in a European Physical Journal or something. This was before the current thing, or European Journal of Physics. It's the other one. It's not a very well-known journal. But if you're interested, I'll try and dig out that paper and send it to you.
Yes, I would like to see that.
Okay.
So please send it to me too. This is Ralph Chamberlain.
Yeah, I will do so. In fact, I could share it with as many of you as you want. But yeah, please ask questions that you may have. And
okay, may I ask one more question?
Yes, John. Please.
It's not really inside this talk, but I just want to ask your opinion. In the free expansion, let's say volume of the left, volume of the right are taken to infinity. So then during some period of time, the current of the particle from left to right may reach some steady state value. I'm not sure about that, but let's say.
So you're extending the cylinder to infinity on both sides.
Yeah, and
okay.
And for some period of time, it may appear the system has reached some steady state current. Then there is a talk of maximum, what is it called? The maximum entropy production, minimum entropy production, all this non-equilibrium discussion. Yeah. Can you say something about that based on your premise?
I'm not sure, actually. The solution, let's see, do we have?
You will have your explicit solution, right?
So this is an explicit solution. I can imagine taking L to infinity and 0 to minus infinity, and deriving something from that. But I can't do it just off the top of my head. It's an interesting question. It will depend, will behave, as you say. I think that's correct, but exactly what comes out, I don't know.
Okay, because there are so many confusing discussions, about that.
Well, of course, if you really move the thing far away, eventually you get further away than the particle can reach in the time t. So that's an interesting question. I'll look at that. That's a very interesting question. I don't know.
May I ask a question?
Yeah, sure. Go ahead.
So, looking at this expression, if I think about thermodynamics or statistical mechanics, it's all for equilibrium, right? And here you have something that is not equilibrium. So during that non-equilibrium process, like what John was describing, that sort of thing, how many of the statistical quantities are still really well-defined or meaningful?
During this expansion.
Yeah.
It's an interesting question, and it relates to the question of how you define entropy for a non-equilibrium system. And what comes out of this is that the density is not, that one expression for the density is not enough. You need a density that varies with x, along the whole cylinder, and there's a corresponding expression here for the density of energy, which is not the same as this. So you have the density of particles varying with time, and if you specify the entropy of it at any given point, you have to specify how many particles are where all along. So for example, if it goes for a little while, say it goes a time t equals tau, so it's 1, and then you put in partitions all along, just 1,000 different partitions, and lock the system into having a certain number of particles, which is different in close to 0 and close to L, and it will have an entropy which should be very close to the entropy of the non-equilibrium entropy. But you
So
obviously
you
need,
basically use local equilibrium to
Yeah.
represent.
so you're going to need a lot more variables to describe this than you would for t equals 0 or t equals infinity. Because in those cases, it simplifies greatly. But even in just expanding an ideal gas, you have to introduce many more variables to describe the density as a function of position and to describe the energy density as a function of position. So it's a much more complicated problem.
If you have to introduce a whole bunch of variables, maybe that's not the right approach to look at the issue then. Right.
Maybe it's not. Maybe there's a simpler way to do it. But as far as I can see, the problem actually has to specify the state. You do need the variables. And if there's a way to get around that, that would be wonderful. But I don't see it.
Thank you.
Tad, go ahead. Tad has a question. Tad? Wait,
there we go. Yeah,
okay.
there we are. Thank you very much. Interesting talk. I wanted to sort of look at the definition of your entropy there. I screenshotted it so I could see that. And my next step is almost the next to last. Oh, the slides are gone. Oh, no.
Whoops.
I was just wanted to say that the next step in my mind, backup one, the formula for SJ for one system. Yeah. I want to take the temperature by taking the derivative of this with respect to E. Is that valid? Is that the right thing to do? What do you get?
Well, if you take the derivative of the second one with respect to U, you get the correct temperature. If you take the derivative of Sj with respect to Ej, you get something very close to the right answer. Because it involves, if Nj is fairly large, the difference between 3Nj over 2 minus 1 and 3Nj is vanishingly small. If you have 10 to the 20th particles, it's negligible. So you do get the right answer if you look at large systems. If you insist upon looking at 2 or 3 particles, you won't get the right answer, or it'll correspond to a different physical situation.
Thank you.
Yep.
Yeah, so the problem is a little bit also messy, right? Because you actually are talking about a microcanonical ensemble.
Yeah.
So your E is naturally not a variable. So you have to think about 2 snapshots at 2 different E values where you are, and you are differentiating between these 2 systems. So it's not really a same ensemble problem.
Well, it depends on how you interpret E, V, and N. If you look at that as a function, and take the formal derivative, it works. If you say, well, how would I actually implement that and find it, you're absolutely right.
Yeah. I have another thing I'm struggling with. One of the things one learns in StatMech is the generalized ensemble theory, which was the Leibowitz, Perkus, and Verlet work of 1967, which points out that all the thermodynamic ensembles in the thermodynamic limit, they give the same results.
Yep.
And lays out the Laplace and the Legendre transform combinations to map the free energies and to map the partition functions in each of these ensembles.
That's correct.
It is valid, of course, only in the thermodynamic limit. But I was just wondering, because you have an exact expression for entropy in the microcanonical case and in the grand canonical case and in the canonical case for that matter, whether you can comment on the corrections that one might have to introduce if one is going to do this kind of a transformation for a smaller system, the kind of system that Ralph might be interested in, because he works on small systems.
Well, these are exact within the microcanonical approximation and the grand canonical approximations. My own feeling is that the thermodynamic limit is oversold. I don't think it's particularly useful. It's convenient for some things. It is quite possible for the thermodynamic limit to give misleading answers in the case of some phase transitions, especially first order phase transitions. So I do not like it that much. In these cases, 10 to the 20th or 10 to the 30th particles are not, the behavior of such a system is not the same as the behavior of the thermodynamic limit. So
I completely concur. That's
yeah.
the finite size effects are important.
Yep.
You know, except for possibly in the grand canonical ensemble. For instance, in the microcanonical ensemble, the entropy should include, well, I think as you wrote it, it's includes the factorials exactly, so that's correct. But usually it's simplified using Stirling's approximation,
yeah.
and there are finite side effects in that and so forth. But I think the way you wrote it, it's quite accurate.
Yep.
Yeah, I'm just more wondering whether one can actually have a finite n version of the generalized ensemble theory. And it seems to me that should be possible because there should be a way to introduce correction terms, right?
You're talking about the thermodynamic limit, or?
No, so generalized ensemble theory is set up for thermodynamic limit, right?
Yeah.
But what if the thermodynamic limit is not imposed? Question is, yeah, go ahead, Ralph.
Well, what Terrell Hill did is he assumed an infinite ensemble of finite systems and assumed that then that infinite ensemble should obey the thermodynamic limit. So the constituents of the ensemble themselves have finite size effects, but altogether they should behave like an infinite system. And so that was his approach. And so I believe it's the correct approach, and it's sort of what we're using as a outline, as a guide to describe finite size behavior.
That's
I'm going
very
to have to go back and review that book.
It's an extraordinary book. I find something new in it every week.
Well, I remember it from many years ago. It was very good. I liked the book very much, but I really haven't used it very much recently. So I will go back and do it.
You are one of the few people who have even heard of it. So,
oh no,
really appreciate that.
Yeah, it's a
no, it's a famous book. He was great.
Yeah, that was I mean, he wrote 2 books, right? There are 2 books he has.
I think so.
2 volumes of the small system book, but yeah, they're that's just because it took them a while to write them. It's there's no real difference in the development. The assumptions are the same. It's just a continuation. It was just the way
I
it was
see.
published.
Any further questions? Sorry, I didn't mean to stop the discussion.
Yeah, I have a question here.
Please.
Yeah, about the right, 1 second. Yeah, the entropy expression for the microcanonical using this Boltzmann method of composite systems. So you yeah, you said
The expression I've got in the top.
right.
Yeah.
Yeah, so it's not extensive as it's written. So
Nope.
I'm not sure what is the origin of this problem, if we could say.
The origin of the problem is that it is uses an assumption that the energy has a specific value, and NJ has a specific value. That it's the microcanonical approximation. If you get rid of that approximation in the second line, it goes away. It becomes exactly extensive. But that's where the problem is.
Right, but for example, we can run molecular dynamics with fixed energy. It's not a.
Yeah, of course.
Yeah, I'm right. So
But,
are you saying such systems do not exist in reality, the microcanonical?
You can run this system, run a simulation of a microcanonical system, which is what you get when you do molecular dynamics, and it will obey that upper level there because it has a constant energy. If the energy is limited, if you're not integrating over the energy, you're missing one of the integrals, just one. And all the other integrals are there, but you're missing one. And consequently, you don't get that extra factor of E. So you have 3n over 2 minus 1 instead of just 3n over 2. So you're missing a factor of E because you're not integrating perpendicular to the surface of constant energy. It has a very small effect if you have a usual macroscopic system, or even a very small macroscopic system, 10 to the 10th particles, but it is there. It has caused a tremendous stir by people saying that this is wrong. I don't know if you have paid attention to the argument that let's see, Dunkel, Hilbert, and Henke, who claimed that the negative temperatures didn't exist, because if you look at this argument and it can be shown to exclude negative temperatures. So the error is in the microcanonical approximation if you push it to the limit, and it's just a microcanonical approximation. That's all it is.
Right. Okay.
Any other questions or points that you want to raise?
Yeah, I was just wondering what is the name of the book you were talking about? Just
the name of
oh, it's an announcement actually.
the name of
Teller.
Oh, I see.
my book.
Whose book are you talking about?
That you were talking about a book, Statistical Mechanics. I guess Teller.
The small system thermodynamics book?
Right, right.
Terrence Hill.
Terrell Hill.
Terrell.
It's been republished by Dover. It's available on Amazon.
Okay.
He published it in 1963 and 1964. It basically lays out finite size effects in thermodynamics in a very consistent way.
Yeah. I do remember that it's good and he writes well.
Well, it's very mathematical. It's difficult for me to understand.
Yeah.
I congratulate you because it's.
Well, I didn't say it was easy for me to understand. It's a beautiful book.
It's amazing. Yes.
Yeah. You can do a search under T.L. Hill.
Yeah, I just found it. Yeah, thank you so much.
Yeah, sure. Okay. If there are no further questions, I would like you to unmute yourself, if I could request you to, and give an applause, if you don't mind, for this fantastic talk. And let's thank him for.
Thank you very much.
Very nice. Very nice.
So you have kicked off the year at a very high level. So enjoy the rest of your weekend and Happy New Year to all of you.
Thank you.
Thank
To
you.
you too.
Thank you very much. Thank you for inviting me.
You're very welcome. Thank you for accepting. Bye-bye.